Good morning, on and all. Today, I am going to take product of sums using Karnaugh mark. For example, suppose that you have a function of ABC like f of a, b, c is equal to ab or bc. AB or bc, that is the function, and the Karnaugh mark corresponding to that is here. This is A and this is BC 0 0 0 1 1 1 1 0 0 1. Okay. AB plus BC means here AB. That means A remains the same and B also remains the same. That means here these two are ones. And C BC means B and C remains the same. That means BC remains A has changed. Now this one. And now these two collectively forms BC and these two collectively forms AB. These two, that means these two collectively forms BC. That means here this one stands for B and this one stands for C, and A has changed. Here for these two, A remains the same and B remains the same. That is why AB plus BC. Now all the remaining elements or these cells contain zeros. Now I am going to have a new expression which is the f of ABC is equal to. Now I am going to have the product of some form. If you want the product of some form of this expression, product of some form, what I am going to do is here instead of grouping zeros, we are going to group ones. For example, here this is a group. This is the first one. Now you have covered 4 zeros and 1 zero is left. That also will cover. That means this is the first group and this is the first group and this group corresponds to. That means for in this group here A changed from 0 to 1. So there is no more A term. And here from this to this, see these two groups. Here 0 0 to 0 1, that means B remains the same. Actually this is C changed from 0 to 1. That means B remain unchanged, and that means this one represents B bar. But in sum of products form, you have to take the negative of the term. That means we have taken zeros instead of 1. That means we have grouped zeros, and hence you have to take here if you are grouping ones, you have to take B bar here. But as you are grouping zeros, you have to negate the letters. That means here actually it is B bar and you have to take B. That means B. That means f of ABC. Now you are going to have product of some terms. That means product of this and product. That means product of these two terms or three terms. That means here sum of products means here this is a product, this is a product, and after that you are taking the sum. Here you are taking some sums and after that you have to take the product. Now first sum is this one. First sum is B. And the next sum is, see, you are going to group this zero, you have to include. For that you have taken this and you have taken this. Okay. So this is the second group. That is the second group, and in that group, say from, that means this is, or this is also a column. From this column to this column or this column to this column, what remains unchanged is C bar. That means C bar remains unchanged, and as these two belongs to the same, row, A bar also remains the same. That means this is 0, and in this group or in this row A bar is same. That means A bar C bar. Actually this group means A bar C bar. Instead of taking A bar C bar, A bar C bar you have to take A plus C. That means A bar C bar the whole bar is equal to A plus C. Actually, we are going to take the dual of this. That is why A plus C. That means we are going to take, actually this one represents A bar C bar and you have to negate it. That means A bar C bar the whole bar is equal to A plus C. That means you are taking A plus C. That is the next term. And B into A plus C. What is B into A plus C? B into A plus C is equal to BA plus BC, which is AB plus BC. Okay, AB plus BC. That means both are same, AB plus BC. And now I'll tell you. Suppose that you have a 4 element Karnaugh map, and suppose that you are going to, this is 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. Okay. Now, if you are taking sum of products form, this is a group. This is group number 1, and this is a group which is group number 2, and see, this is a group which is group number 3. That means f of a b c is equal to, f of a b c is equal to, say for the first group here what remains the same. That means from 0 to 1 to 1 1 1, that means 0 1 to 1 1. That means CD. This is C bar D and this is CD. That means D remains the same. That means first one is 1 plus 2 plus 3. 1 is, what is 1? 1 is from this column to this column, 0 1 to 1 1. What remains the same is D. That means D into, from this row to this row, what remains the same? That means A bar. That means this is A bar D. And what is 2? 2 is this column as a whole. That means in this column, A changes from A to A bar and B changes from B bar to B or B to B bar. That means A and B terms cancel each other. A and A bar is there, so that will be cancelled, and B to B bar, that also will be cancelled. And CD terms, that means this is, what is this? This is C bar D, and that is C bar D plus, and the third term is, what is third term? Third term is this one to this one. That means in this row, what remains constant? A B bar. A B bar remains constant. That means 1 0 remains constant, and 1 represents A and 0 represents B bar, A B bar. And from this column to this column, what is changing? That means the D term is changing. That means 1 and 0. What remains? C. That means this is A B bar C, and that means this is A bar D plus C bar D plus A B bar C. Okay, that is f of A B C. Now, if you are taking the dual of this f of A B C, that means we are going to take the sum of products form. Sum of products form, here see, I am going to take this as a group. This is the first, second, third. This is the fourth group, and I'm going to have a group like this. That means this one and this one I am going to take a group, and that is the fifth group. And here I am going to have a sixth group. That means f of ABC is, I am going to take the product of sums form, that means that is 4 into 5 into 6. 4 into 5 into 6. What is 4 into 5 into 6? What is 4? 4 is in this column, what remains unchanged is C bar D bar. C bar D bar. You have to take the dual of that. That means C bar D bar is, that means you have to complement that C D, and in between, instead of multiplication, you have to include addition. That means here C bar D bar changing to C plus D. That means 4 is C plus D into, what is 5? What is 5? 5 is this one and this one, and from here to here there is a change. What remains unchanged is A bar. That means B changes from D bar to B. What remains unchanged is A bar, and from this column to this column, what remains is 0 0 to 1 0. What remains the same? D bar. That means A bar D bar. And if you take the dual of this A bar D bar, that is A plus D. A plus D into, what is 6? What is 6? 6 is, what is this? 6 is, all the elements of this one remains the same. That is AB. That is AB. AB remains unchanged, and from this column to this column, what remains unchanged? That is C. That means AC. That means when you are taking the product of sum, when you are taking the sum or dual of this becomes A bar plus B bar plus C bar. That means this is C plus D into A plus D into A bar plus B bar plus C bar. This is, both are same. A bar D plus C bar D plus A B bar C means C plus D into A plus D into A bar plus B bar plus C bar. If you multiply this and take the sum, you may get this. I will try that. Now we are going to discuss implementation of sum of products form. For example, F is equal to AB plus BC plus C bar D, and here we can use AND OR implementation. That means using only AND and OR operations you can do that. That means here we have an AND gate, and if you are going toward the inputs, this is, if this is A and this is B, this is AB. And if you have an OR gate, if you are giving two inputs A and B, this is A or B. That means this is AND and OR gate. That means simply you can do this. That means A and B is given to an AND gate, B and C are given to an AND gate, C and D bar, C bar D. That means C, this is a NOT gate also is there. This is NOT gate, and if you give A, you will get A bar here. That means using AND OR and NOT gates, you can easily implement this. And our point of view, we are going to implement this using only NAND gates. That means NAND implementation. NAND implementation. NAND implementation means in NAND implementation, in the first level, that means these are the products. AB is a product, BC is a product, and C bar D is a product. That means you have to take as many number of NAND gates as number of products. That means here you have a product, here you have a product, and here you have a product. And the NAND gate is like this. That means this is NAND gate, and the input to the NAND gate is A and B. These are the inputs to. That means here you are going to take AB and those are given to as the inputs of this NAND gate, and in the second level, this is not in the first level itself, you are going to give B and C, and now another product also is there. In that case, you are going to give what is C bar and D. Okay, and these are the outputs. Then we have another NAND gate here, and these are given as inputs to the NAND gate. This is the output, and the output will be AB plus BC plus C bar D. Say, what is this output? That means what is this output? AB, and A into B the whole bar. That means AB or the whole bar. And what is this? This is taking the product, then taking the complement. That means BC the whole bar, and this is C bar D the whole bar. These are the outputs from the first level: A B bar, B bar C, and C bar D the whole bar. When these three are given to this, now you are taking the product of these three. That means product of those three are AB bar into BC bar into what is C bar D the whole bar and the whole bar. That means after multiplying these three, you are going to take again. You are going to take, that means these three are multiplied, and after that you are going to take the complement. That means that is NAND. That means this is the function. When you are doing this, what will happen? A bar B bar AB bar dot BC bar dot C bar D bar the whole bar is equal to A bar dot B bar the whole bar is equal to A bar plus B bar, right? A bar dot B bar the whole bar is equal to A bar plus B bar, which is as per De Morgan's law. So here you are going to take this as A and this as B, or this as X and this as Y. Okay. Now the first one is X and the second one is Y. Then as per De Morgan's law, X bar dot Y bar the whole bar is equal to X plus Y. X bar dot Y bar the whole bar is equal to X plus Y. Likewise, here I am going to take this as X and this as Y. And what is this? What is this? This is F is equal to AB bar dot BC bar dot C bar D the whole bar is equal to, if you are taking this as X, this is X and this is Y. Okay, that is X bar plus Y bar the whole bar is equal to X bar plus Y bar the whole bar is equal to X plus Y. So you are taking this as X, this as X and this as Y. Here this is actually X dot Y the whole bar, which is X bar plus Y bar. This is X dot Y the whole bar, which is X bar plus Y bar, means this becomes AB bar dot BC bar whole bar plus C bar D bar the whole bar. That means X bar plus Y bar. X dot Y the whole bar is equal to X bar plus Y bar. That is X is AB bar dot BC bar and Y is C bar D the whole bar. That means this is what? This is X bar and this is Y bar. That is, here C bar D bar, the whole bar is equal to, this will become CD plus, this is not CD, this is C bar D plus, what is X bar dot Y bar the whole bar? X bar dot Y bar the whole bar is equal to X plus Y. This is AB plus BC. That is why you have AB plus BC plus C bar D. That means you get AB plus BC plus C bar D. That means this is the NAND implementation of sum of products form. That means in the first level you have as many number of NAND gates as the number of products, and finally you have a single NAND gate, and the output of the first level NAND gates are feeded to the second level NAND gate, and the output of the second level NAND gate will be the sum of products. Okay, that is the NAND implementation of Boolean expressions. And in this NAND as well NAND, if you are going to take the complement of this, what you are going to do is, here this is an AND gate, and this is, if you are giving C here and you get C bar here, that means you have a 2 input NAND gate, and C dot C is again C, and when you are complementing that you get C bar. That means to complement a literal using NAND gate, just to give it as input and take the output. That means the output will be the complement of the input. This is an AND gate. That means here, suppose that you have A, B and C. Here, if this is C, here you are going to have an AND gate. You are going to provide this to an AND gate, and the output is fed to this. Okay. That's why this is the NAND implementation of sum of products form. Now we are going to have product of sum form. For example, suppose that you have product of sum form like, say, suppose that your function is the product of sum. This is product of sums form. Product of sums form. That means A plus B into, say, B plus C into C bar plus D. Suppose that this is the input. You are going to realize this. You are going to realize A plus B into B plus C into C bar plus D. A plus B into B plus C into C bar plus D. That means here now you have one term, second term, and this is the third term. These three, so you have three terms, and you are going to take the product of those three terms. So for that you have, so this can easily be done using AND gates and OR gates. You can simply do that. That means if you are taking an OR gate, and if you are giving inputs A and B, and the output will be A plus B, and if you are providing B and C, the output will be, if you are providing B and C, the product will be B plus C, and if you are giving C bar and D, the output will be C bar plus D. Okay. If these three are fed as inputs to an AND gate, this is an AND gate, the output will be A plus B into B plus C into C bar plus D. That can easily be done using AND gates, OR gates and NOR gates. But we are going to have a NOR implementation of product of sum form. NOR implementation. NOR implementation of expressions. NOR in the sense, just like our NAND implementation, here in the first level, you are going to calculate the number of sums. Here you have 3 sums, and in the first level, you are going to have 3 NOR gates. This is gate number 1, this is gate number 2, and this is gate number 3. This is a NOR gate, and as the inputs to the NOR gates, you are providing AB, BC, and here it is C bar D. That means now you have 3 sums, and that's why you have 3 NOR gates in the NOR gates in this level. You have 3 NOR gates in this level, and now here you have, what is this? A plus B the whole bar. Here you have B plus C the whole bar, and here you have C bar plus D the whole bar. Now you are going to feed these 3 into another NOR gate, and here you are taking the sum. Okay. Now that sum will be A plus B into B plus C into C bar plus D. So you can verify that answer using your De Morgan's law and all, just like your NAND implementation. Now here in this case, what you are going to do is, here in the final expression, you are going to calculate the how many sums are there. Here you have 3 sums, so 3 gates, 3 NOT gates are there at the first level. This is first level. In the first level, you have 3 NOR gates, and as the inputs, you have to give simply the literals. Here A plus B, so that's why you are going to provide A and B. Here you have B plus C, you are going to provide B and C, and here C bar and D, you are going to provide C bar and D. Okay, then these are the outputs, and outputs of all these NOR gates are fed to another NOR gate, and the output will be F is equal to A plus B into B plus C into C bar plus D. Okay, that is the NOR implementation of this product of sum form. And for taking the negative or complement of 1, see, simply you have a 2 input NOR gate, and if you give C here, what will happen? C bar is the output. Why? C plus C. What is C plus C? Here C plus C is C itself. When you are complementing that, you get C bar. That means using NOR gate, using a simple NOR gate, you can easily realize C bar. And here you have C bar. That means if you are taking this input, and if you are providing this, or if you are giving this to a NOR gate, the output you can fit. That means this will be, if this is C, this will be C bar. Okay. That means using only NOR gates also, we can have the implementation of a Boolean expression. That means for implementing sum of products form, NAND implementation is you can use NAND implementation, whereas in the case of product of sum form, you have to go for NOR implementation of expressions, Boolean expressions, or NAND gate realization is there, NOT gate realization